Hi ladies, this is Blaufuss here. This is lesson 2.8 and it's about graphing linear inequalities in two variables. So in class we just talked about graphing absolute value functions, and before that we were graphing linear equations. But now we're going to look to see what a graph would look like for an inequality. So we have a couple key terms. The first one is a linear inequality in two variables, and this is an inequality that can be written in the form ax plus by is less than c, ax plus by is less than or equal to c, ax plus by is greater than c, or ax plus by is greater than or equal to c. So for all of these forms, a and b and c are all constants. X is an x-coordinate solution and y is a y-coordinate solution. So the solution of a linear inequality, stemming from that first definition, that's the ordered pair x or y that's true when your values for x and y are substituted into one of these four forms, whatever form you have for your inequality. And then the last term that we have is called half plane, and this is a boundary line that divides the coordinate plane into two pieces. So here are our three vocab terms: linear inequality in two variables, solution of linear inequality, and half plane. Now let's actually look at what these things mean. So you can follow along in your guided note sheets. So with graphing inequalities, the graph of a linear inequality in two variables is the set of all points that represent the solution. So we've been graphing inequalities just with one variable, and if we had something where we would say, x is greater than 1, on our number line, we could graph it by saying it doesn't include 1, but x is greater than 1. So anything greater than 1 would be a solution. So 1.2 would be a solution, 2 would be a solution, 100 would be a solution, 99.5 would be a solution. All of those are solutions, and on our number line, that's the part that we shaded. We said, okay, here are all our solutions. Solutions go on forever as long as x continues to be greater than 1. And then all these other ones over here, these are not solutions. All the way up till 1, those are all non-solutions. So in a coordinate plane, instead of having one dimension, now we have two dimensions. We have an x and a y coordinate, and we have two variables to represent those coordinates. So on the graph that you see on your note sheet, you see this dotted line right here. This is our boundary line. So this is the line that divides our coordinate plane into multiple sections, into two half planes, and the shaded half plane is the solution. So here, 3x minus 2y is greater than 2. These are all the points where that is true. So when x is 3, y is 0, that is the solution for this. So when x is 3, 3 times 3 minus 2 times y is 0, that is greater than 0. And if we multiply it out, we get 9 minus 0 is greater than 0. That is a solution. A dashed boundary line is like our circle here on our number line. It means that it does not include the points on the line, but a solid boundary line is like our dot on our number line. It means it includes the points on the boundary line. So the points on a solid boundary line are solutions, and points on a dashed boundary line are not solutions. So let's try a couple where we're checking our solutions. So it says check whether the ordered pairs 3, 2 and -1, 4 are solutions for 4x plus 2y is greater than 6. So to do this, we're just going to substitute our x and y coordinates into our inequality. So our inequality 4x plus 2y is greater than 6. Let's see if 3, 2 is a solution. So our x coordinate is 3. So 4 times 3 plus 2 times our y coordinate is 2. Is that greater than 6? So this is the first one. 12 plus 4. Yes, that's greater than 6. 16 is greater than 6. So yes, it is a solution. Now let's look at the second one. It says -1 and 4. Is this a solution? So let's substitute our values in. So 4 times our x value, which is -1, plus 2 times our y value, which is 4. Is that greater than 6? 4 times -1 is -4. 2 times 4 is 8. Is that greater than 6? -4 plus 8. 4 is not greater than 6. So the second one is not a solution. So on your own, try ordered pair 6 and 2 and ordered pair 3 and -1 into our linear inequality in two variables, which is 2x minus y is less than or equal to 8. If it's true, it's a solution. If it's false, it's not. So please pause the video while you work and unpause for the solution. So if you substitute the x and the y values into the inequality, for letter A, you would have got 10 is less than or equal to 8, which is not true. Therefore, 6, 2, the point 6, 2 is not a solution for the inequality 2x minus y is less than or equal to 8. And the second one, if you substituted in 3 for the x value and -1 for the y value, you would have got 7 is less than or equal to 8. That's true. Therefore, the point 3, -1 is a solution for the inequality 2x minus y is less than or equal to 8. So the next step beyond determining whether or not a point is a solution for an inequality, we can graph. So just like we graphed the inequality of one variable on a number line, we can graph the inequality of two variables on a coordinate plane. So our first step is to graph the boundary line for the inequality. And to do this, we are going to graph it as if it were true. So instead of saying y is less than 2, we would graph the line y equals 2. And that's our boundary line. So if it says that it's less than or greater than, we're going to use a dashed line. If it says it is greater than and equal to or less than or equal to, we're going to use a solid line. After we graph the boundary line, we're going to test a point that is not on the boundary line. So it can be any point, any x or y point, but it cannot be on the boundary line. And if it is a solution, then every part of that half plane is the solution. If it is not a solution, then every point on that half plane is not a solution. So often we use 0, 0 as a quick, easy test point, but if 0, 0 is on the boundary line, we have to choose a different point. So let's try a couple together. So here we're going to graph the inequality y is less than or equal to 1 in the coordinate plane. So the first thing we're going to do is graph the boundary line. So let's graph y equals -1. So here's y at -1. All of these points are y at -1. Now, since it says strictly less than, we need to use a dotted line. So y, not including y at -1, y is less than -1. So now let's pick any point in either of the half planes. It doesn't matter, you get to choose. Let's pick 0, 0, just because it's easy. So does this point, 0, 0, satisfy this inequality? Well, let's check. We don't have an x, but our y is 0. Is 0 less than -1? No. 0 is not less than -1. 0 is greater than 1. Therefore, this whole half plane is not a solution. So we need to shade in the part that is a solution. So here's our section that is a solution. So again, we used a dotted line for our boundary line because that is not included in the solution. But anytime y is less than this boundary line is our solution. Let's try another one. So here we have two variables. And the first thing we want to do is graph this boundary line. So again, we have strictly less than, so we're going to use a dotted line. But we're going to graph the line 3x minus 2y equals -6. So this is in standard form. So the suggestion for you can put it in sub-intercept form if you'd like, but with standard form, generally you just graph the x-intercept and the y-intercept. So our x-intercept is when our y is 0. So 3x equals -6. Our x is -2. So let's graph that point first. Our x is -2, our y is 0. And then our y-intercept is when x is 0. So -2y equals -6. Our y-intercept is 3. And these are 2 points on our boundary line. And again, since we are talking strictly 3x minus 2y is less than -6, we need to use a dotted line. Oh, okay. It's not perfect. So I would suggest using, when you're doing this on your own, use straight edges. Okay, so there's our boundary line. Now we need to pick a point, any point, it doesn't matter. Again, 0, 0 is a pretty easy point to deal with. So I'm going to choose this point, and if it is a solution, then every point on that half plane is a solution. If it's not a solution, then every point on the other half plane is my solution. So 3, 0, 0, my x coordinate is 0. 3 times 0 minus 2 times 0. Is that less than -6? 0 minus 0 is 0. Is 0 less than -6? No. So that is not a solution. So every point in the other half plane is where I will shade. This is my solution. So those are all of the points where 3x minus 2y is less than -6. So those were linear inequalities, but now let's look at graphing an absolute value inequality. So again, with our absolute value inequality, our general form for an absolute value function is y equals a times the absolute value of x minus h plus k, where our a is our stretch or shrink, our h is our horizontal shift, and our k is our vertical shift. So graphing the absolute value function, -3 times the absolute value of x minus 1 plus 2. First thing we want to do is, again, graph our boundary line. In this case, it's our boundary equation, or our boundary equality. So first thing we want to do when we graph absolute value functions is to find the vertex. So our parent function, remember, the vertex is 0, 0, and then it goes up 1 over 1 in both directions. But with a horizontal and a vertical shift, our vertex changes. And here we can also see that we have an A, which in class we discovered if it's negative, flips the graph upside down, and if it's greater, the absolute value of A is greater than 1, then it vertically stretches it out. So this absolute value function is going to look a little bit different than the parent function, but that's okay. We can still graph it. So our vertex, our x-coordinate of our vertex is 1, because that's our h value. And the y-coordinate of our vertex is 2. So we're going to graph that first. And then since our a is 3, it's -3, we know that that if we move over to the right 1 unit, we're going down 3 units. And if we move to the left 1 unit, we're going down 3 units. So here's what our absolute value graph will look like. So if this is our absolute value graph, and we want our y to be greater than -3 times the absolute value of x minus 1 plus 2. Actually, these should be dotted lines, so I'm going to switch that. Okay, here we go. I had to make those lines of my absolute value boundary line. I had to make those dotted because, again, we're working strictly, strictly with y is greater than -3 times the absolute value of x minus 1 plus 2. So now we're going to pick any point. It doesn't matter which one we do. Again, 0, 0 is a pretty easy point, and since it's not on our boundary line, we can choose that. So we're gonna see if that is a solution. If it is a solution, then every part of that half plane is going to be shaded, and if it's not a solution, then the other part of the half plane is going to be shaded. So we're going to substitute in 0 for y. 0 is that greater than -3 times 0 minus absolute value of 0 minus 1 plus 2. Move this up a little bit. Okay, so 0 is that greater than -3 times the absolute value of -1 plus 2 is 0 greater than -3, and the absolute value of 1 is 1. So -3 times 1 is -3 plus 2. So is 0 greater than -1? Yes, it is. Therefore, 0, 0 is a solution. That means that every part of this half plane, every part outside of our boundary line, all of this is a solution. So these are all of the points. These are all of the points where y is greater than -3. Where y is greater than -3 times the absolute value of x minus 1 plus 2.